How do apps like Discord, WhatsApp, Slack, and massive multiplayer games instantly update millions of users in real time? I mean, why don't stock trading platforms just refresh the page every single second to show live prices? How does Uber continuously track drivers moving across a sprawling city in real time? And how do companies like Google, Netflix, and Amazon maintain persistent communication between millions of devices simultaneously? Well, the answer is one of the absolute most important technologies behind the modern real-time internet: WebSockets.
This is the protocol that literally transformed the web. It took us from slow, clunky request-response communication into persistent, real-time, bidirectional communication. And look, if you're preparing for back-end engineering, distributed systems, or system design interviews at companies like Meta, Microsoft, Google, or Uber, this is a topic you absolutely cannot ignore. But don't worry, we're not going to learn this through boring, dry networking theory. In this explainer, we'll use anime-inspired storytelling, cinematic high-contrast visuals, and real-world engineering scenarios to make concepts like WebSocket handshakes, persistent TCP connections, bidirectional messaging, and frame structures feel incredibly intuitive.
So let's look at the core problem. On the left, you've got traditional HTTP. It's essentially a rusty, discrete conveyor belt. It demands a brand new, resource-heavy handshake for every single request. Over time, you're wasting megabytes of bandwidth just sending headers back and forth. But on the right, WebSockets offer us something beautiful: a persistent, high-speed, two-way glowing neon tunnel. You do one handshake, and from then on, zero-latency data streams.
To actually engineer these systems, we need a roadmap. Think of this blueprint as our master plan. It maps out the 3 primary lifecycle stages of a WebSocket connection. First up, the handshake forge. Second, maintaining that persistent TCP tunnel. And third, masked and fragmented delivery. By the end of this explainer, you're going to start thinking exactly like a distributed systems engineer.
But right before we initiate that handshake, there's a really brilliant piece of engineering design we have to talk about. WebSockets don't require you to open up crazy new network configurations or punch holes in firewalls. They elegantly piggyback right on top of existing HTTP infrastructure. They use standard WS on default port 80 and secure TLS encrypted WSS on port 443. It's a completely frictionless upgrade path.
Let's dive into Phase 1, the Protocol Upgrade Handshake. The whole process kicks off with what looks like a totally standard HTTP GET request, but it's carrying some very special mandatory headers. The client sends an upgrade WebSocket header paired up with a connection upgrade header, basically saying, hey, let's switch gears. But the absolute most critical piece of this puzzle, that would be the sec WebSocket key. Now, don't be fooled. That sec WebSocket key is not a password. It's actually a randomly generated base64 encoded string that is totally unique to this exact handshake. The server absolutely needs this key to prove that the client actually understands the WebSocket protocol and isn't just a confused HTTP client blindly trying to connect. Welcome to the Shah-Jah-Shah reactor. When the server catches that client key, it executes a highly specific cryptographic sequence. It takes the client's unique key and concatenates it with a globally recognized predefined UUID string. It takes that combined glowing string of data, fires it straight through a SHA-1 cryptographic hash function, and then encodes the final result in base64. This creates the sec-website-accept key. It's an undeniable mathematical proof of understanding. Once the math checks out, the server fires back its HTTP response. Status code 101, switching protocols. This is it. This is the dramatic moment the neon tunnel officially opens. But keep in mind, there's a strict validation protocol here. If the client receives anything other than a 101, or if that accept key doesn't perfectly match the hash it was expecting, the connection is terminated instantly. Security and protocol compliance are absolute.
Which brings us to Phase 2. Deconstructing data payload frames.
All right, the tunnel is open, but how does data actually travel through it? It travels in extremely lightweight, highly structured units called frames. Inside this exploded view of our high-tech data packet, you can see that every single bit has a precise engineering purpose to control message state and network routing. We've got the FIN bit, RSV bits, the opcode, the mask bit, and the payload length, all wrapping like a protective shell around our core payload. Let's translate these abstract bits into concrete engineering realities. The FIN bit, that simply tells us if this is the final fragment of a message. The RSV bits are basically reserved for future protocol extensions. The opcode dictates the actual data type we're sending. And the mask bit indicates whether cryptographic obscuring is turned on. It is amazing how just a few tiny bytes of overhead can manage massive, complex data streams so effortlessly.
Think of the opcode as the commander of the frame. It signals exactly what kind of payload is hidden inside. Are we looking at a green UTF-8 text frame for a real-time chat app? Or maybe a blue raw binary frame for a multiplayer game state? Or, crucially, a magenta ping or pong frame? Ping and pong are essentially a high-speed game of digital Marco Polo. They act as the heartbeat of the system, constantly verifying that the server or client on the other side hasn't just vanished into the void.
Moving on to Phase 3, Network Hazards and Fragmentation. This brings us to a classic high-level system design interview question. If our secure tunnel is already established, why does the protocol strictly enforce masking on every single frame sent from the client to the server? I mean, what exactly are we hiding from in our own tunnel?
Well, we are hiding from what we call the proxy hazard. See, before WebSockets were globally standardized, the internet was absolutely full of legacy network infrastructure. Specifically, HTTP caching proxies. These proxies try to be smart. If they see plain text flowing continuously from a client, they might incorrectly interpret our persistent WebSocket stream as just a long series of normal HTTP requests. They try to cache them, and that leads to catastrophic stream corruption. The solution? Masking. Think of it as optical camouflage for our data packets. The client applies a random masking key to the payload, completely scrambling its appearance. To those legacy HTTP proxies, the data just looks like completely unpredictable, uncacheable noise. So they ignore it and let it pass right through. It's a beautifully brilliant workaround to bypass outdated internet infrastructure.
But wait, there's another hazard lurking in the dark, the overload threat. Imagine a user uploading a massive file over our persistent connection. If we just send that file as a single gigantic message, we risk a critical buffer overflow. We could completely exhaust the memory limitations on either the client or the server, crashing the very real-time infrastructure we just worked so hard to build.
The elegant engineering solution to this is fragmentation. Instead of sending one massive block of data and hoping for the best, we chop it up. We send fragment 1 with the fin bit set to 0. That tells the receiver, hold on, wait for more. Fragment 2, fin equals 0, wait for more. Finally, the last chunk is sent with fin equals 1. That's the signal to the receiver to assemble the entire payload. This protects our system buffers and allows for the safe, gradual delivery of massive data streams.
Finally, Phase 4, Real-World Distributed Systems.
Let's anchor all of these deep, technical protocol mechanics back to the massive scale apps you use every single day. From instant messaging on WhatsApp and Discord to the incredibly fast sub-millisecond positional updates required in competitive multiplayer gaming. From multiple users drawing simultaneously on a live collaboration canvas to the perfect real-time updates of financial tickers on global stock exchanges. WebSockets power some of the most critical real-time infrastructure on the modern internet. It is quite literally the engine of the live web.
So that's WebSockets, the technology that transformed the internet from static, clunky communication into a fluid, real-time interactive system. We explored how browsers and servers establish persistent communication channels, how bidirectional messaging enables instant updates, and how distributed systems maintain millions of simultaneous real-time connections efficiently. And honestly, once you truly understand WebSockets, you begin to understand the massive engineering challenges behind building low-latency distributed systems at global scale. This is exactly the kind of engineering knowledge that separates someone who merely builds applications from someone who engineers real-time internet infrastructure. If you enjoyed this explainer, make sure to like, subscribe, and share it with anyone learning back-end engineering, networking, distributed systems, or system design. But before you go, ask yourself, the next time you send a message and get an instant reply, exactly how many masked, fragmented frames did it take to make that magic happen? We'll see you in the next explainer, where we'll break down another powerful architecture concept used inside the world's biggest tech companies.